The generalized linear model, or GLM, is a flexible generalization of ordinary linear regressions that allows for response variables that have error distribution models other than normal distributions. The GLM generalizes linear regressions by allowing the linear model to be related to the response variable via a link functions and by allowing the magnitude of the variance of each measurement to be a function of its predict value. The 5 components of GLM following: first, the response Y, the linear predictors eta equals to x beta. The distributions of Y should be exponential dispersions family. Then, the link functions G mu equals to eta with mu expectations from the Y, and a prior weight 1 per C. In line with this, the likelihood principle following from the Birnbaum from the 1962, first, the classical likelihood functions contains all the information in the observed data about the fixed parameter, provided that the assumed stochastic model is right. Thus, if the model is correct, likelihood captures all the information in the data for analysis, and the model checking is possible. All necessary inferential tools can be derived from the likelihood. In GLMs, the likelihood inference can process via integrated weighted least square equations. Also, the least squares methods in regressions becomes the maximum likelihood procedures in the GLMs. The iterative weighted least squares is a general algorithm to find the maximum likelihood estimations and standard deviations in generalized linear models. There are several ways to derive it, but the one that has been developed in these functions via is the New-Repson's method. It consists of making a Taylor expansions in the score functions, the first derivative of the log likelihood around the maximum likelihood estimations. In addition, generalized linear models attempt to accommodate variance heterogeneity and asymmetrics, non-normal behavior by offering a range of distribution types that cover at least the more common mean variance relationships. GLMs are also useful for obviously non-normal data, such as binary data. The log likelihood surface must be reasonable quadratic in a region about its maximum point for most parametric inference methods, such as model-based standard errors, confidence intervals, and likelihood ratio tests to be reliable. As we introduce the notions of generalized linear models, 2 important issues surface: the distributions of the response and the model that relates the mean response to the regression variables. These 2 issues are not independent of each other, because certain types of models are more appropriate for some distributions than for others. An important unifying concept underlying the GLM is the exponential family of distributions. Members of the exponential family of distributions all have probability density functions for an observed response Y that can express in the form: the log likelihood expressed as log L theta Cy equals to theta transpose Y minus beta theta divided by C plus C when beta theta is cumulant generating functions. The mean of mu equals to expectations for the Y, which is B accents theta. The variance denotes to var Y equals to C beta double accents and theta. In addition, the distributions of Gaussian Poisson binomial gamma given as follows. Then, to the iterative weighted least squares for likelihood, there are 8 ways. First, specify a starting value for the beta. Say beta power 0 with k equals to 0. Second, the compute adjusted linear predictors, which is eta to the power k plus 1 equals to x beta power k, and our mu power k plus 1 is equal to y to the power of the minus 1, eta to the power of k plus 1. Keep in mind, g here is a length function. Third, compute adjusted dependent variable by doing derivatives. 4. Fit the weighted linear regressions. And it is necessary to compute the x transpose wk plus 1x and beta hat. Step 6. Put estimated coefficient as beta power k plus 1. Step 7 is repeating from step 2 to the step 6 until the convergent. And finally, after convergence, we report the beta hat and variant beta hat. Keep in mind, the iterative weighted least squares is the extensions of least squares method to generalized linear models. To measure the residual, first we can do the calculating of unscaled deviance and unscaled deviance components, do the standardized deviance residuals, or we can make the presence residuals. Keep in mind that all of distributions is different to calculating of deviance the components, which is you can see from this table from the distribution normal, Poisson, binomial, and gamma. In another hand, D star is the log likelihood ratio statistics and P star is the Pearson chi-square statistics. Regarding the hat values, the generalized linear models have the hat matrix, which is x bold, x transpose, wx power minus 1, x transpose w, where w is the diagonal from the derivative from the eta e, derivative mu e power square, and the variance of ye. The diagonal elements of H are the hat values denoted by ki. The studentized residuals adjust for the hat values and are obtained as Re divided by root 1 minus ki. Therefore, we can use the unscaled deviance to estimate the dispersion parameter as follows. Then, we can apply the generalized linear models by using the albatross analytics. First, upload the file, do the browse, and choose the crack growth data. To begin with, the crack growth data from the experiments where crack length in inch are measured on the compact tension steel test or CT test, operated in different laboratories, followed by Hudak et al. In 1978. And we have 4 variables. First, y, which is the instruments of crack length, and the crack 0, initial value of crack length, cycle, number of cumulative loading cycles, and specimens, 21 metallic specimens. And we can create our models by following model eta equals to log mu equals to alpha plus beta crack 0. Click the regressions, choose the GLM, choose the response variable, the distributions, Gaussian, link functions, identity, and response variable y. We select the independent variable crack 0. Choose the distributions gamma, the log functions log, and this is our model summary. Then lastly, we choose the family gamma, the link functions log, the optimizations by the IWLS, and the number of iterations is 5. We can justify our model is right or not first by see the p-value from the coefficients, which is the crack 0 is less than 5%. And from our models, we also can compare with the AIC or BIC. The next steps, we do the offset variable. We see the robust standard error and make the confidence interval. So, the confidence interval from our coefficients appear like this. To check the our models, you can click the model checking plot. Then, to get the predictions for our models, just click predictions. On the other hand, you can compare the second model by select the different distributions. For these cases, we choose the Gaussian distributions with the link functions identity and click run. So we have two different models here. Model first by using distributions gamma and model 2 by using distributions Gaussian. The next example, we choose the trend datasets, page 130. So the trends data related the accidents data in the UK between the 1975 and 2003, following by aggressive 2007, which is there are four variables: x, numbers of years since the 1975, y, the number of accidents between trains and road vehicles, t, distance of train travels, and log t, logarithms of t, and we can rate our models as follows. To analyze the data, same like previous steps, open the albatross, choose the GLM, choose the distributions Poisson, click functions log, check the offset variable, choose the log t, and click run. And our models will be appeared like this. We have p-value which is less than 5%. Click model checking plot. This is the scatter plot of our residuals, and this is the predictions from our models. Same. In the next example, we try the crab datasets. Therefore, the data from the study of nesting horse crabs, which investigate factors that affect whether the female crab had only adult males, called satellites, residing near her, following by James Brookman in 1996. And this data including 6 variables. First, set, the number of satellites, y, indicator of whether a female crab has any satellites, weight, width, the color, 1 is medium light, 2 is medium, 3 is the medium dark, and 4 dark. And spine, 1 both good, 2 1 broken, and 3 both broken. In line with this, p is the probability of the y equals to 1. We can write our models eta equals to log p divided by 1 minus p, and the alpha plus beta with. Click the regressions, choose the GLM, log it, choose the response variable y, the distribution is binomial, and the link function is logit. Click run. And this is our model from y with. P-value is less than 5% for the width variable. Next, we do simulations by snoring datasets. The data based on the epidemiological survey to investigate snoring as possible risk factors for heart disease refers to P.G. Norton's and E.V. Dunn in 1985. The variables including the yes, number of people who have heart disease, no, number of people who doesn't have heart disease, X is the snoring levels, 0, never, 2, occasional, 4, nearly every night, 5, every night, and N, yes plus no. When the P probability Y equals to 1, we can write our models eta equals to probability P, C accents P, which is the alpha plus beta X. Click regressions, choose GLM, and probability model. Choose the response variable yes, the independent variable X, the distributions binomial, the link functions is probit, and we check the binomial denominator by AND. Click run. This is our model from the probability model. As you can see, the p-value is less than 5%. To comparisons, we make the generalized linear model, choose the response variable y, choose the response variable yes, the independent variable x, the distributions is binomial, the binomial denominator and click run. So this is the comparisons for our model with the probit. First, by using the link function logit, and our second model by using the link functions probit. At the same time, we can check our model's residual and the predictions. The next example, we select the tennis datasets. Tennis datasets results of matches among 5 professional tennis players between the January 2014 and January 2018. Following by accuracy in 2019. The fit models provides a ranking of the players, and it is also estimate probabilities of win and of loss for matches between each pair of players. This table presents the professional tennis players, and we can write our model as follows. Open the Albatross, upload file tennis, and our dataset will be appear like this. But first of all, we create our variable and write our new variable name as and write the expressions nij plus ngi. Click run and our new variable will be appear like this. Therefore, to analyze, click regressions, choose GLM, choose the response variable nij and select the independent variable of the tennis player professional. The distribution should be binomial. The binomial denominator is the n. Check the no-intercept model, click run. And this is our model from the tennis professional player. From the coefficients from our models, only Djokovic and Federer, which is the p-value less than alpha 5%, which is significant. Then, the Murray and Nadal is not significant. The p-value is more than 5%. Click the model checking plot to see our residuals and click the predictions to predict from our models.